Hey guys, welcome to the third week of Math 4000, problem solving for Putnam. Well, this week we will talk about geometry, and my goodness, when I was preparing this lecture, I was like, it's so much to cover. So what I'm going to do is the following. I will cover two things today. I will try to cover as much as I can from Euclidean geometry, something that supposedly you have done in high school, some of it, but also I would like to cover some vector geometry as well. And actually, with the vector geometry, well, some things are done in Calc 3, but some things are not done in Calc 3. But anyway, let's get started. I will start with some things about the Euclidean geometry, and then I will show you some problems. Anyway, I'll just cover at first some basic stuff. All right, so let me say it again. So this is about geometry. And what we're going to do today, like I said, I will cover only two things. So geometry. So I'll divide this into four parts. Euclidean geometry, and you'll see they're connected with each other. Vector geometry, and this will be covered as much as I can today. The third part will be complex numbers. You'll see applications of complex numbers in geometry. And probably I'll cover this in another video, maybe tomorrow. And the last part, which is again, all of them are connected to each other. You'll see, well, I will take one problem and I will try to solve it with different methods. I will use Euclidean geometry to solve it, then vectors to solve it, then complex numbers, and even analytic geometry. And here I will include also, let me put it like this, in conics. Okay, let's get started. So we will cover only these two today. So let's start with the first one, Euclidean geometry. And in fact, when I talk about Euclidean geometry, I will stick to the geometry of triangle. I'll say the geometry.
Oh, that's under my name.
By the way, I think Nadia, you have your mic. Your mic is on. All right, geometry of the triangle. All right, let's draw the triangle. This is, this this should be a triangle, ABC, right? This is how we denote a triangle, and this will be the side lengths of the triangle. So we'll denote this BC is A, CA is B, and AB is C, right? Before we talk about important lines in a triangle, I would like to say a few things. Well, I will have the following notations. I will denote by S A plus B plus C over 2. This will be the semi-perimeter. And K is what we call the area, will be given by this formula, which probably you know about it. S times S minus A times S minus B times S minus C. This is what we call Heron's formula. Formula for the area of the triangle. Of the triangle, and sometimes we denote it like this, ABC, right? So again, notations, S is the semi-perimeter, we said this. So let's write it again. And K is the area. Okay, let me be specific. This is little s, a semi-perimeter of triangle ABC. And this K is the area of the triangle ABC. All right. So that's the formula. These are the two formulas that you need to know, right? All right. And there are some other things. Maybe I should draw in that. Okay, let me draw. This is altitude, right? And let's call this altitude HA. And also the area of a triangle, K, can also be A times HA over 2, which is the same if we draw the, if I do the same thing here, and I do the same thing here, right? So this is perpendicular here, perpendicular here. Of course, they'll have to meet somewhere, and we'll talk about these points. There's the same V times HB over 2, the same C times HC over 2. It doesn't matter which altitude you consider, right? We already know this formula. All right. In fact, they do meet at a point here, which is called H. H is the orthocenter of the triangle. So H is the orthocenter of the triangle ABC, right? So the intersection point of the altitudes, it's called H. Anyway, we will talk about this. As you can see, H has a formula. I can even write HA, the altitude, I can compute it. It's easy, right? So from here, we can say that HA is 2K over A, right? HB is 2K over B, and HC is 2K over C. All right. So that's what you know. This is the altitude. Okay, but there is also another formula for this. Let's, if you look at this angle, and you know all this stuff, but anyway, I'm just gonna say it again. Also K is, if you want, C times A, or let me write it like this, is AB times BC times the sine of the angle between them, which is ABC, everything over 2. Or if you want to write this, is C times A times, let's call this alpha. So this is alpha here. So if I denote this by alpha, then this is sine of alpha over 2. All right. Now, let me say something. Let me draw the triangle again. Oh my goodness, this is not even a straight line. But anyway, you'll forgive me for this, right? Okay, let me draw this again. This is crazy. All right. So this is a triangle again. And now what I want to do is the following. So I want to say something. Let me draw. Let me say this is D here. So this is, let me draw the altitude again. E and F. And this is we said that the intersection point is H, which is the orthocenter. All right, but also I can draw something else here. I can draw the circum circle. Oh my God. All right, imagine that this is the circum circle. Of the triangle ABC. And oh my God, this is insane. Anyway, I'll leave it like this. And now let me draw something else. Let me draw, well, let me draw something which will be called the incircle. And you'll see that something happens here in the circle of the triangle ABC. Well, there are two other points coming here. The center of the circum circle, let's call this O, so it's somewhere, let's say here, O, right? This is, anyway, maybe I should not. O is the center of the circum circle. I have a question. Can you hear me well? Okay, great. And now what I'm gonna do, I'll put this point here, I, somewhere here, let's say. Oh. Right? I is the center of the incircle. And you'll see that something is going on with this I. Well, maybe I should draw a different picture, but you'll see that this I, we said that H is the intersection of, in fact, I'll draw it here, right here, is the intersection of the altitudes, but this I will, okay, here's a point, let's say A1. Here is another point that goes through I. And touches the, no, in fact, this is, sorry, this is A1. This is A1, this is B1. And again, as you can see here, if I draw, oh my. Okay, this is what. And if I draw now from C through I, and I'm touching all the way to here. Let's say this is C1. Well, guess what? These guys, A1, B1, C1 are the legs of the bisectors. So A1, AA1, BB1, CC1 are the bisectors of the triangle ABC, are the bisectors of the triangle ABC, and they have one point in common and have one point in common. And which is I, which is the incenter I. This is where they meet up, right? Okay, let me denote this H. Let me put it somewhere right here. So we have this H, we have this I, we have this O. There's one point missing. I'll explain immediately. Oh my. But now I would like to say a few things. There are two formulas here, because you see, let me denote R is the radius of the circumcircle, and little r will be the in radius, or, oh, in fact, no, let me put it like this. Okay. This will be the radius of the will be circumradius. So from now on, I'll refer to these two like this. And little r will be the radius of the in circle, which is in radius. And these two guys have a formula, two formulas. Now R will be the product of ABC over 4 times the area, and little r will be K over S, the area over the semi-perimeter. So keep this in mind. Anyway, you might, and also there's another thing between them, what we call R, the circumradius is greater or equal than 2 times the in radius, and this is what we call Euler's inequality. You see, Euler has done many things in math, including this little thing. And if you want to express all this together, and if you want to use Heron's formula, this will be equivalent with, this is equivalent with the following inequality, which we have done probably, or we talked a bit. I'll write it in this way. The product of B plus C minus A is less or equal than the product of A. Right? When I talk about the product, I mean B plus C minus A times C plus A minus B times A plus B minus C less or equal than ABC. That's what I mean. And anyway, you can use this. I'll leave it to you as an exercise. Use AMGM to solve this. But the thing is that you use AMGM 2 by 2. In fact, let me say it. So B plus C minus A times C plus A minus B is less or equal. Okay, let me take the square root. Then B plus C minus A plus C plus A minus B, everything over 2. And this will be, well, this is nothing else than just C, right? And now you multiply, you write the analogs, you multiply them, and there you go. All right, let me draw I want to draw, so as you can see so far, well, I hope I'm not going too fast. I hope you can, is the pace okay? Anyway, there will be a lot of information today. That's why, thank God we record the video so that you can watch them later on. Let me draw because I want to define one more thing. And now this time I'll draw everything. So this is a triangle ABC. All right, here we go. I'm going to draw the altitude. I'm going to draw the bisector. And I'm going to draw the median. In fact, maybe I should, no. Maybe I should do this with a different color. Let me draw the bisector with red, or I think, no, I used this is the bisector, and this guy is the median. Anyway, the median will divide this into 2 parts, but it's not, doesn't quite look this way. Maybe more, a bit more accurate. And this will be the median here. Okay, so let's call this, the first one is D, whatever. Then this guy, let's say we said it's A1. And this guy, we said it's A prime, right? All right, so once again, we say that, well, AD is the altitude from A, right? AA1 is the bisector from A, and AA prime is the median from A. These three important, and now we can draw the other 6. But let me tell you one thing. At some point here will be H. In fact, let me draw another one so that okay. This will be H here. Or maybe I should put them at the end so that now if I draw another bisector, let's say from B, will be like this. This will be the in circle, and at some point, if I draw another median, will be somewhere here, right? And there will be 3 important points here. This is H. Well, this will be, they're not quite collinear, but anyway, in fact, there are 4 of them. This is I. I don't know where to put it. Anyway, I'll put it here. And this will be G, the centroid. But also there will be if I take the circumradius, there will be O here. Let's say somewhere here will be O, right? And it says one thing, well, this is not quite, okay, maybe O should be, oh my God, the picture is not the best, I could tell you that. Okay, and O is somewhere here. O is somewhere here. Well, it says the following: H, G, and O are collinear, and this is what we call Euler's line. So H, G, and O are on the same line. And this is what we call Euler line. Euler's line. Anyway, we'll see a problem where we will use this. See, okay. Okay. The G is the intersection of the medians, right? And let me say this again. Maybe I should put here, just let me write, so B, E, then B1, and then B prime. Anyway, and you can draw the other 3. The moral of the story is the following. The intersection of the medians you know what the median is, right? It divides the segment into 2 equal parts, the opposite line, right? Is G, which we call the centroid of the triangle ABC, right? And this G has this very nice property that it divides the median into, so it's 1/3 from the base and 2/3 from the vertex, right? That's one nice thing about it. That's what you need to know about but probably you know this, right? Okay. Well, the question is, can we find out the lengths of the well, the altitude we already know. So we know what, and let's, okay, I will denote the following notations. HA, like I said, is the altitude from A. LA will be the length of the bisector from A. Okay, maybe I should say here the length of the altitude. Let me be specific. The length of the altitude from A. This is the length of the bisector from A. And MA will be the length of the median from A. And in this way, you can define the other, right? You can define the other, the analogs from B and from C. Okay. Well, the question is, there is a formula for these three. We already know what the formula is for the altitude. We can express it in terms of the area. But before I even go and in fact, let me see. Before I even go and find out write the formulas for these three, let me remind you something, because I would like to. So you already know the bisector theorem, I hope. Let me remind you. My God, I cannot cover everything that this was supposed to be done probably in high school, but anyway. I don't even know what the material for K-12 is at this point. I don't know if they do anything, so. But anyway, so let me draw the bisector here, and with this, say this is AA1. So AA1 is the bisector. Right? Oh my goodness, that's exactly what I need. My pencil has only 5% anyway. Well, let's just wait for 1 or 2 minutes. Well, I would like to say one thing here, is that when you have a bisector, there will be something will happen with the ratios here. And let me say exactly what it is. It means that AB, let me write this. AB over AC is the same as BA1 over A1C. That's the bisector theorem. Or if you want to write it in this way, AB is C over B is the same as BA1 over A1C. So this is the bisector theorem. And now I would like to do a couple more things. Well, this is just a little bit of geometry, but I would like to cover the most important things. Now I would like to give you some formulas. In fact, I would like to give you the Stewart's theorem, and you from Stewart's theorem will be. But before that, I forgot about this. There's also some other things you need to know about a triangle. And this is very, very important, especially when we will talk about vectors, especially when we talk about the dot product or the cross product of vectors. There are two things that you need to know. And these two things are the following. Is the Sine Law, which says the following. In any triangle ABC, well, we have that, I'm going to write it with red, A over sine of A is the same as B over sine B and it's the same as c over sine c. And moreover, this is 2 times the circumradius. So that's the sine law, and we will use this in some applications, you will see. And now the cosine law says the following: in a triangle ABC, we can express the cosine of A is b squared plus c squared minus a squared over 2bc. In fact, let me write this with the color too, so that you can. So this is cosine of A is b squared plus c squared minus a squared over 2bc. That's and the analogs, right? And the analogs. So that's these are the two formulas these are a must. I'll show you some examples once I'm done with the theory. I'll show you some examples of how to use these formulas. In different problems. Especially, I will need the second formula when I will try to derive some properties for vectors. But anyway, all right. Now, I'd like to give you something that we will call Stewart's theorem. And from this, we can derive the formulas for the length of the bisector or median or whatever. And let me again draw the triangle. And now what I'm going to do, I'm going to take M to be a point on this. And now we can do the following. I have the triangle ABC. And M is a point on a segment on a point on BC, right? And now what I'm going to do, I can compute the following. Then we have the following. Let me write it here. AM squared times BC, right, is the same as AB squared times MC plus AC squared times AMB minus a BM times MC times BC. That's the Stewart relationship. This is a very nice one. Anyway, I don't remember it. It's not hard to remember, but I don't usually remember it because the way you derive it is the following. I'll leave it to you as an exercise. You can look at this angle. We can call this alpha if you want. And you look at these two triangles. There's one here. And you look at the big one too. And the main thing is just to apply cosine law. In the triangle ABM with angle alpha, and the same again, cosine law and in the big triangle ABC with angle alpha. So you have cosine, you can write cosine of that angle in terms of the side lengths of in the triangle ABM. And you can do the same thing for the big triangle. And then you'll just do the computations and you'll derive exactly this formula, which I hope I wrote it. Okay, I think, yeah, that's correct. Anyway, And from here, you can derive anything. Man, I don't, it's so much to cover from Stewart's relation. We can derive the following. And like I said, I'm going to leave this to you as an exercise to do. For example, the length of the bisector will be 2 times BC over B plus C times cosine of A over 2. And the length of the median will be 2 times B squared plus C squared minus A squared, everything over 4. I hope these are correct. Anyway, you can just use Stewart's theorem. You know what the bisector is, you know how to express the cosine of, and also there are some trigonometric formulas that you need to take into account. The fact that, let me just say them here. But I think these are done in Calc 1 as well. But let me remind them to you, is that sine squared of x plus cosine squared of x is 1. Sine of 2x is 2 sine x cosine x, and cosine of 2x is cosine squared of x minus sine squared of x. Anyway, there are some others. You can, you know what, cosine x plus y is cosine x cosine y minus sine x sine y. Anyway, just you can recap this from any Calc 1 course. All right. There are some other things that I would like to cover. Man. Menelaus and Cezar's theorem. Did you guys do this in high school? Did you cover Menelaus and Cezar's theorem? Do you remember anything about this?
No.
Nothing. Wow. Anyway. So let's start with Menelaus' theorem. Yes, I did Menelaus and Cezar's theorem. Well, some people knew it when they were like in 7th grade, and like not even in high school. Well, I knew it before, but they also covered in freshman high school. So let me draw the picture so that you can see it better. Oh, my God, I'm drawing these lines like. All right, so I have the triangle ABC. And now what I'm gonna do is the following. Look at this. This is C here. And I'll have this line here, let's say, I'll have this line, which will cut, of course, 2 of the points inside the segment. Let's say I'll have here X, Y, Z. We call this X, Y, Z a transversal, wherever. But what you need to know here is the following. Menelaus' theorem says plain and simple that these guys, these points, X, Y, Z, are on the same line, are collinear, basically on the same line, if and only if the following holds true. I'm going to write this with bx over c or x times c times c times y over ay times az over bz is 1. This product is 1. So this is if and only if. That's what it basically says. So keep this in mind, because Cezar's theorem will come into play. And Cezar's theorem says the following. So this is it says the following, and I'm going to draw again a picture here. A, B, C. And I'm going to draw some Chevians here. And they will intersect at this one point. Let's say here.
A little bit.
Say that again?
You scroll up a little bit. Okay, right there.
So AD, BE, and CF. And let's say they intersect at this point P. So we say that these lines, these Chevians, what we call them, they intersect at this one point P. And the theorem says the following: AD, BE, and CF conquer at the point P if and only if, guess what happens? Well, as you can imagine, if and only if AF over FB times, now I'm looking at this segment here, then I'm going here, and then here, times BD over DC times CE over AE. Guess what? This product is 1. And this is just a consequence of Menelau's theorem, because if you look, if I look at this triangle, let's say, if I look at this triangle right here, let's say ABD, this guy here, FPC, is the transversal, you see? And I apply Menelau's theorem 3 times, and I multiply all of them, and then guess what? It will give you 1. Anyway, all right, guys, I think, all right, this is what I want to cover. Wow, my God. You see, it's a lot of things to cover and just, and now let's do problems. So problem, I'm just going to stick to Euclidean geometry, and then vector geometry and complex numbers will appear. So problems. And now the first problem that I have in mind is the following. Okay, I'm going to hit you hard. With the following problem. This was, in fact, let me do problem 1. Ouch. And this was a Putnam B6, okay, 1982. And the problem states the following. Let me see the statement here. The statement says the following. Let K of X, Y, Z denote the area of a triangle whose sides have lengths X, Y, and Z. Okay, for any two triangles with sides A, B, and C, and A prime, B prime, C prime, respectively. Prove that, and we have to prove the following inequality. The square root of k ABC plus the square root of k A prime B prime C prime is less or equal than the square root of k of A plus A prime, B plus B prime, and C plus C prime. Okay, I want you to look at it for, let's say, for a couple of minutes. So what I'm interested in, how do we compare the sum of the areas? Well, they're in square root with the sum of the, or with the area of the triangle when we add the sides of each of the two triangles. I want you to look at it. So you can draw two triangles. Right? So what would be the first thing that will come to your mind when you look at this? Well,
Could we prove it using the radii, the two different radii, the circumradius and inradius?
You're going a little bit too far. Well, the problem is it's quite direct.
What does it want to use Heron's theorem?
Exactly. I was thinking of Heron's formula. Well, we look at the statement. Try to think, when you have a problem, try to think as simple as possible. So you say, look at the statement. You have KXY, Z is the area of the triangle whose side lengths are X, Y, and Z. Well, if you think about it, what options do I have? Just use the Heron's formula, because Heron's formula will give me, is a formula that expresses the area of the triangle in terms of the side lengths of the triangle. So why not use this? Okay. And then you will see that something happens. So let's see. Let me denote S to be A plus B plus C over 2. This will be the semi-perimeter of the triangle ABC, right? And S prime is A prime plus B prime plus C prime over 2. This will be the semi-perimeter of the triangle, let's say A prime, B prime, C prime, right? Let's call it like this with the side length. All right. Now, Heron's formula says the following. Let's say for K A ABC, let's put it this way, is the square root of what? Of S times S minus A times S minus B times S minus C, right? And for K, A prime, B prime, C prime, this will be the square root of S prime times S prime minus A prime, S prime minus B prime, and times S prime minus C prime. Okay. Okay. Right. Great. But now I want to, you see, I have the square root of this. It will be this. Now if we denote, let me use the following notation. Let's say T is S minus A, U is S minus B, and V is S minus C. Can you tell me what the area of, what is KABC, the square root of this? Well, actually, no, just tell me the KABC will be what? Will be what? Will be the square root of what? What are these guys? S times S minus A is already this, but S will be what?
P minus A.
Say that again?
P minus A, I believe.
Be careful a bit.
It'd be T plus A.
Actually, let's leave
Oh,
it
sorry,
like
T
this.
plus A.
No, let's just leave it like this. So it's S times what? Times T times U times, and then K A prime B prime C prime is what? It will be what? S prime T prime U prime V prime. Now the question is, what is K of A plus A prime, B plus B prime, C plus C prime? Look, I want you to tell me this. Will be what? Will be the square root of what? Well, the semi-perimeter will be what? It's clear that it's S plus S prime, right? Because you add the two, right? But now what about the others? What is A plus A prime will be what? Using this notation, these notations. Okay, and I forgot to say one thing. Okay. Maybe I should be okay. Okay. Do give me, because, and the note, maybe I should have, the note T prime is S prime minus A prime, U prime is S prime minus B prime, and V prime is S prime minus C prime, right? Then we, K A prime B prime C prime is nothing else than just what? Is the square root of S prime T prime U prime V prime, right? And now how can we express this K of A plus A prime, B plus B prime, C plus C prime? This will be the square root of what? Can you tell me? Based on, well, the semi-perimeter will be what? Will be S plus S prime, right? What about A plus A prime will be what? We're using the notations above. Will be T plus T prime. Exactly, and so on. Correct, just like, yes, exactly, just, like Nadia says. And now, keep in mind that I have to prove the square root of this. So our inequality will be equivalent to what? Is equivalent to what? Let's see. Keep in mind to prove that the square root of this will be equivalent to the following. The fourth root, because it's the square root of the square root of what? Of STUV plus the fourth root of S prime T prime U prime V prime is less or equal than the fourth root of S plus S prime T plus T prime U plus U prime times V plus V prime. Well, guys, does this ring a bell to you? This baby right here, does this ring a bell to you? It should ring a bell to you. There was a problem. It's not quite. Well, instead of me doing, well, you can do it if you don't remember something that we did. You can just square it and the computations will be painful. And I don't want to lose time in doing the computations here because I want to solve other problems as well. But it should ring a bell to you because I did one particular problem. And if you look, there was this problem number and actually I did it. If you look at the videos, I did one of them. Does anybody remember what problem I'm talking about? Do you guys remember what was in the list? Where is the list? I have it here with the worksheet with. Do you guys remember problem 3? It was a Putnam A2 2003. Well, it's funny because it's do you remember? For A1, AN positive and B1, BN, and we did this positive. We have that the end root of the product do you remember this? Well, if you take n equals 4, what do we obtain? This was solved. In recitation 1. In fact, I think it was one of the second problem that I solved. Right? If you look at the videos, I solved it. Well, does the inequality follow immediately from this one? Well, for n equals 4, what do we get? It's exactly this guy here. Guys, is it clear what I'm talking about? You seem like mute. Like.
No, it makes sense. I just didn't think to use that inequality.
Yeah. Jack, is it clear?
Yeah.
Okay. Jared?
I am following.
Gabriel?
Yeah, I think
Okay.
so.
All right,
I
great.
get what you're doing. I just didn't think of it.
Okay. You see, that's it. You already solved this. So you need to remember some of the problems, at least some of the ideas from the problems. Anyway, so to avoid these computations, to ugly computations, raising everything, squaring, and then squaring again, and then applying AMGM over and over again, just it's immediate from this problem. It's just n equals 4. Anyway, this holds true for a much more general, not just for the square root of the triangles. And in fact, it holds for any convex bodies. It's called Brun-Minkowski's inequality. I'm not getting into details about this. I don't want to lose time with this kind of stuff. Anyway, now that's it. That's the end of it. Oh my goodness! Since I'm in a bit of a rush, I want to do more problems, but let me do some interesting ones. Ooh, ooh, ooh. All right, let me do this one. Again, this is a nice one. So this was problem A2. So what did we call this? So problem 2. This is Putnam A2. 1985, I think. Anyway, the statement says the following. Let T be an acute triangle inscribe a pair RS of rectangles in T as shown, as below. And let me draw the picture. So this is the triangle, right? And I'm going to inscribe in the following way. This would be the rectangle, the first one. And then I'm going to inscribe here another one, like this. So this is S and this is R. Let A of X denote the area of polygon X. Find the maximum value or show that no maximum exists for of A of R plus A of S over A of T, where T ranges over all triangles and RS over all rectangles as above. Okay, look at the statement. That's the statement. In fact, we can generalize this. And you will see how everything will apply. So I will we will generalize the problem. And I'm going to draw the following picture. me draw the following following triangle, right? And what I'm gonna do is the following. I'm gonna put some rectangles here, right? Then I'm gonna put another one. And I keep going. And I keep going. Okay, let me put here another one. And I keep going. Okay. All right. So let's call this is R1. Oh. This is R1. This is R2. This is R3. And we keep going. This will be Rn minus 2. And this is Rn minus 1. And what we want to do is to find you're almost there, not quite 1, but you will see it's some, yeah, you're right, actually, you're right, yeah. Something like this. Anyway, you will see. Okay, and now we want to find the maximum value of the following expression: AR1 plus ARn minus 1, everything over A of t, right? For n greater or equal than 2. And now let's look carefully. You see I have this stack of rectangles here, right? And now I want to analyze this picture very, very carefully. What I'm going to do is the following. Let me draw an altitude, and because I want to divide this into 2 parts. Look. Right? So I'm going to draw an altitude. So let me write this. The altitude of the triangle we'll divide this, divides into 2 right angles, right? 2 right angle triangles, divides T into right angled, right triangles, let's say. And I'm going to denote this, let's say it's U on the left. So let's call it, so this is U, and let's say V on the right. And V on the right. Actually, you'll see this is not a hard problem. It's easier than you think. You just have to analyze a bit the picture. That's okay. All right, so I have these 2 triangles. Look here, and what I'm going to do here, I'm going to denote these guys, all these triangles here. So this is by, okay, I'm going to look at this triangle here, right? Look at this one, and let me do another, and look at this one here. And this is what I'm going to do. I'm going to look at these, look at these, look at these, at this guy, and again at this guy. And the same thing I'm going to do here. Look at this triangle, and these are right angle triangles. Look at this guy here. Look at this guy, and this guy. All right? And I'm going to denote it in the following way. This will be V1. Oh my God. This will be V1, V2, V3. This will be, the last one will be Vn. This will be Vn minus 1, Vn minus 2. And the same thing will happen here. This will be Un, Un minus 1, Un minus 2, U3, U2, U1. Right? Because if you add all this together, will give me the area of the entire triangle. And now let's analyze together. Let's be very careful here. I want you to look very, very closely at the picture. Okay. So as you can see, UIs, let me just say it. So UN is the, how should I say, the small right triangle above our n minus 1, and Vn, well, on the left, okay, you understand what I mean, right? It's UN is on the left and Vn is on the right. On the left, let's say. And then this guy is a small right triangle above or n on the right. Okay. Again, I don't want to lose the picture. This is important. And now I would like to say a few things about this. Let's look at the big triangle here. You see, it's this triangle T is split into two triangles. Well, it's quite clear that let's denote this by A, this altitude of A, right? And the altitude of each one of them is AIs. As you can see, these are AI, A3, oh, sorry. This is, so the these will be AIs, right? A1, A2, A3, and so on. The same will happen here, it will be the same, right? These are equal. A1, A2, A3, and so on. That's the, is it clear? Is the picture clear for everybody? Okay. Try to keep it in your mind, right? It's a stack of rectangles and it keeps going. And then I have some triangles, right angle triangles there. And I want you to look either way. You can look on the right, you can look on the left, whatever. If you look at those small right triangles, they're similar. Each one of them is similar to the left or the right right triangle, right? If you look at them. Well, I use right in 3 different circumstances. Anyway, right? Okay. Now, let's see. Is there a way to express the area, and I'll leave it to you as an exercise, the area of any UIs or any VIs is AI over A, everything squared, because these are times AU. And the same goes for VIs. I would like to explain this a bit. Is AI over A squared times AV. Well, these triangles, any triangle VI, any one you pick is, as you can see, it's similar to this big right triangle, right? And well, if you take the areas, it will be just this formula, right? You just express the area of each one of them, right? And then you will derive this formula. I'll leave this to you as an exercise to look at it. It's very, very simple. It's extremely simple. And now, guess what? Now, we can add everything together. So we have, let's add everything together. The sum from I of AIs plus the sum of AVIs is what? Well, considering all this, this will be, it will be what? It will be the sum of AI squared over A squared, right? We can factor this. Everything times what? Times AU, A of U plus A of V. But the area, the sum of these two areas is nothing else than the area of the big triangle. So it's the area of A of T, right? Is this clear for everybody what I'm saying here? Because this T is the disjoint union of all these RIs, UIs, and VIs, right? All right, beautiful. And now, keep in mind that what I want to find is I want to go back, I want to find the value of this guy here. Keep in mind this. Okay, and now we have the following. What do we have? We have that A of R1. In fact, let me write it. The sum of A RIs over A of T will be what? Can you tell me? What is this guy? You know what? Just for the sake of computations, we can assume that A is 1 if you want, or anyway, it doesn't really matter. So the sum of AIs will be what? Isn't this like A of T minus, right? The sum of A UI plus the sum of A of VI everything over A of T, right? And now this is nothing else than just 1 minus 1 minus what? Minus the sum of maybe what? Okay, this sum this will be, so it's A of T minus the sum of these two. If we look above, this is AI squared over A squared, right? Times A of T over A of T, which is nothing else than just 1 minus the sum of AI squared over A squared, right? But now, well, it doesn't matter. We can, well, without loss of generality, we can assume A equals 1. It doesn't really matter. A is nothing else than, keep in mind that this A is nothing else than the sum of AIs. Keep that in mind, right? So this A, which is the sum I had to say this, maybe I should have, is the sum of AIs, if you want. In fact, okay. Keep in mind that this A is the sum of AIs. Just look at the picture. You see A1, you see A1, if you look at each rectangle, A1 plus A2 plus A3 plus so on, it will give you, this will be AN here, right? This guy here, it's AN. It will give you A. All right, that's beautiful. And now guess what? The last thing we need to do at this point, well, this is nothing else than just 1 minus the sum of AI squared over the sum of AI everything squared. But does this ring a bell to you? By the Cauchy-Schwarz inequality, we have what?
The fraction is going to be less than 1, right?
Keep in mind, there is 1 over n somewhere. Actually, wait. What do we know? We have that the sum of AI squared is greater or equal than the sum of AI squared over n, right? Keep in mind we have this n here. So this fraction, if we can write it equivalently, we can say that this fraction right here is what? Is greater than 1 over n. So the minimum will be what? So this is the minimum, right? So with negative, it will be less than. So 1 minus the sum of AI squared over the sum of AI everything squared will be less or equal than 1 minus 1 over n. And this will be the maximum. And the question is, why is this the maximum? Is it attained? When is it attained? Which is attained when we have equality in Cauchy-Schwarz inequality. When do we have equality in Cauchy-Schwarz inequality? Well, when those are proportional, which is attained for all these AIs equal to 1 over n. So that's the maximum value. Well, I generalized it in and actually Nadia had this idea that is approaching 1, but right? This is what you said, right, Nadia? So if you take infinitely many, if you take n as large as possible, this will indeed, the maximum will be 1. So yes, you are, but we have a finite number of them. All right, so this is what we, well, you can, this is just Cauchy-Schwarz here, right? I gave you this inequality, I think, in lecture 1, I think. And in the case, in our particular case, for n equals, what is our case? N equals what? For our problem, be careful, n equals what? Not 2, it's 3. Because we have one other. So the maximum value is 1 minus 1 over 3, which is 2 over 3. Anyway, I overgeneralized this problem, but you could have done it. But I want you to see the big picture. Sometimes it's good to see the big picture. Is the problem clear for everybody, guys?
Yeah, I see how you got it.
See, the only thing you need to, and I'll leave this to you, is to these two here written in green. I want you to look for this. This is a beautiful problem. I had so many other problems to cover, but probably I'm going to do some other videos because this is very, very nice. All right, guys. I think we should stop here for today. I'll send you some other videos with the problems in geometry anyway. We'll see how much I should cover, but and keep in mind that I want to make an announcement. On Friday at 5 p.m. we'll have a special recitation. Jack would like to present you a couple of problems in geometry. So anyway, I'll keep you posted. Thank you very much.